Okay, welcome back for this final session for today. And tomorrow onwards, I think you'll have your favorite topics, I believe. So everyone wants to learn about neural networks, right? Anyone here who doesn't want to learn, who's more interested in things like support vector machines, hidden Markov models? Anyone? Or anyone who wants to learn Bayesian ML, more purist things?
I am.
Sorry? Are we going to be learning? No. I don't think we'll have enough time. There may be, but I don't think it's on the schedule. Yes. Okay, so we'll resume where we stopped just a few minutes back. We write y is equal to fx plus epsilon. Epsilon is normally distributed with mean 0 and variance sigma squared. It's IID measurement noise, right? So we also can then write p of y given x to be normally distributed with mean fx and the variance sigma squared, right? This is where we had what we had already in the previous lecture, right? So I'd also shown you that this is the generative view or the graphical model to understand linear regression. You have the parameters theta, you have the variance or the observation scale sigma. Given an xn, you are able to generate yn, right? For each yn, you get xn and theta. These are used to get the f value, right? And on f, you add the noise, which is coming from this mean 0 sigma scale normal distribution, right? That's the generative view. So why do you think yn is shaded whereas xn is not shaded? What do you think shaded could mean here? So yn is the observed value. So observed nodes are shown in shaded values. And then we have this sort of a rounded rectangle around xn, yn. What do you think this is indicating? So we're using the same set of parameters theta across x1, y1, x2, y2, x3, y3. And why can we do that? Because the data is IID, right? So we've repeated this same story again and again, again and again, again and again, again and again. But I hope that this really gets into your head. The next time in the interviews you're asked IID or when you're thinking about models IID. So fortunately or unfortunately for you, the HMM lecture I'll be taking that. And there the data is not IID, right? So that's why I want you to understand IID very nicely before we go on to non-IID based settings. So this is indicating that for each xi yi pair, you can generate the data as follows. Yi is a function of xi and theta I, and then you add the observation noise sigma. Okay, this was the question where we had stopped. I want you to be able to calculate the likelihood of the data given the parameters theta, right? Now, what is the data set? The data set is x1, y1, x2, y2. Why is x in boldface? X is a vector, right? It can be multidimensional. It can consist of multiple numbers, multiple scalars. It's a vector. Why is y not in boldface? Because y is a scalar, right? You could have had x equal to the temperature of this room, the number of occupants of this room, and y could be the energy consumption of this room. Right? So y is a scalar, x could be a vector. And then the question was, what is the likelihood? The likelihood is probability of the data given the parameters theta, right? Did anyone get a chance to work that out? Okay. Okay. Okay, so you're thinking in the reverse way, or you're thinking in the way in which Ashish explained. So that's one way to approach. you start off with the loss function. So what you said is you started off with the loss function directly. I'm saying that can we maximize the likelihood and derive the loss function? So we did the same thing for the coin toss, right? We figured out the likelihood. Let's go back to the coin toss example. I think it's useful to view this again and again. Probability of head equal to theta, probability of tail equal to 1 minus theta, probability of the data set given theta is probability of D1 given theta, D2 given theta, so on and so forth, all of them multiplied IID, which is equivalent to theta to the power nh into 1 minus theta to the power nt. That's the likelihood that you obtained. And then you maximize this function or maximize the log of this function or minimize the negative log likelihood, and you obtain the loss function and the MLE parameters. That's the same thing which we want to do now, but the only difference being we have an x and y set of parameters. Right. So probability of the data set given theta, can I write it as probability of y given x and theta? Why can I write it that way? That's the first question. The data set it's itself x and y, right? Why can we write it as probability of y given x and theta rather than probability of x comma y given theta? Yes. And so x is firstly known, right? We don't consider it to be random, right? X is given to you, it's considered known. Y is what you're trying to estimate. So y is ending up here as being the thing which you are trying to predict given x and theta, right? So therefore you can change this conditioning a little bit. Now, can we again apply the IID because the data is IID is IID. So we first break this down into probability of y1 through yn given x1 through xn and theta, right? Now, can we write this as a product of yi given xi and theta, right? Because that's what we see, that's what we did a few seconds back for the coin toss also, right? Essentially, this particular line, probability of d1 through dn given theta is probability of d1 given theta, d2 given theta, so on and so forth. The same thing when we do for the linear regression problem. We write it in this way. So this particular symbol means that we're multiplying from n equal to 1 to n, right? So this is probability of y1 given x1 and theta multiplied by probability of y2 given x2 and theta, and so on and so forth, right? So we write it that way. Now, why do we write this particular expression? That this is equal to this is normally distributed yn with mean xn transpose theta, and the scale is, and the variance is sigma squared. How do we get from this step to this step? How so yeah, that's a good question. For now, let's just assume that sigma square is a known term, just to simplify the calculations. There are some nuances to it. For the purposes of this specific summer school and this specific lecture, I think it's fine to just assume that sigma square equal to 1. Let's just keep it that way. It's a known constant. But why can we write it this particular way? That's the first question. Why can I write the log likelihood? Why can I write the likelihood in this particular way? So what is the relationship between y and x? Does everyone agree on this particular line? Probability of y given x, a scalar input x, so single scalar input x, a single vector input x, and scalar output y is normal with y random variable y distributed as with mean fx and the variance sigma squared. So we have done this earlier also. Let me repeat this. You start off with x, right? In this case, x equal to 60, right? you get f of x. F of x is a line, right? Theta naught plus theta 1x in this case. F of x is a line, you get that line. Your y is normally distributed with f of x, with the mean of f of x and some known variance, right? So this orange square in the middle is f of x. And this distribution for y is normally distributed with mean f of x and variance, some known variance. Right? Does everyone get this? Any questions on this? Right? So if you have questions, please ask now, because for logistic regression, this is slightly harder than this particular slide. The probability of y given x is a normal distribution of the random variable y given the mean fx and the variance sigma squared. Scroll up. Yes. Yes. Which curve? The orange one? Sorry? The blue color? The yellow color, right? So I have to go back to the previous. So that's just the normal distribution. Let me actually just explain it. So we write x is normally distributed with mean 0 and variance 1. Is this the normal distribution with mean 0 and variance 1, right? If I had written x is normally distributed with mean 5 and variance 1, that would have looked like right. So here x, random variable x, is normally distributed with certain mean and certain variance, right? But in the slide that you had seen, you first have some x, right? Corresponding to each x, you have a f value. This is a f, right? Now think of it as, let me see if I can actually, no. I was trying to see if I can rotate my screen and you'll see it. No, you won't, you'll still see it the way you're seeing it. So you have got the value of x. So let's say this is x1, x2, some xn. Right? This is some x of I. Correspondingly, you have f of x of I, right? Now your y values are normally distributed with mean f of x of I, and this is some variance. So here the x, in this particular case, when we generally understand the normal distribution, we look at it from the, like with the random variable x, right? Here y of I is normally distributed with mean f of x of I and variance sigma squared, right? So if we had taken some other point, right? Does everyone understand this? Any questions in this? Yes. So coming back, what we're trying to obtain is probability of d given theta. D is x1, y1, xn, yn pairs. So probability of d given theta is equal to, we first write it as x, sorry, probability of y given x and theta. We can write this as, because x is known to us, right? Now we can further break this down as y1 comma y2 yn given x1 x2 xn comma theta. And because of the IAD assumption, we can write it as y1 given x1 comma theta, probability of y2 given x2, so on and so forth, yn given xn and theta. Right? Does everyone agree with this particular line? Right? Now the question is, let's just simplify the question. What is P of y1 given x1 and theta, right? So firstly, we write that, we've seen this, right? Yi is normally distributed with mean f of x of I, and the variance is sigma squared. So therefore, we know that y1 is normally distributed with mean f of x of 1 and the variance sigma squared, right? Now what is f of x of 1? What is f of x of 1? So f is a straight line, right? And because it's linear regression. So what is the expression for f of x1? So it's theta naught plus theta 1 into x, right? In general, so did Ashish discuss the data augmentation? Oh, sorry, not the data augmentation. Adding an extra rows of 1, extra columns of 1 to x. Did we discuss? We did discuss, right? So I'm going to write this as theta naught theta 1. So firstly, we need, let's just look at the dimensions, right? This has to be 1 cross 1 vector, right? Now theta is theta naught theta 1. It's 2 cross 1, right? And x dash, which is the new x, is also 2 cross 1. Now you have two 2 cross 1 vectors. You need to get a scalar from them, which is 1 cross 1. What do you do? Transpose what? So can you just write this as x dash transpose theta, right? Because x dash transpose theta would be 1x into theta naught. Both these things are equal, right? So 1 into theta naught plus x into theta 1, right? And that's what we had over here, right? That's, so all of these things are the same, right? This has to be x1. That's the only thing, right? Any questions till now? So I can now just go over these slides and actually just go over a little quicker. Right, so we have written till this point. that the probability of data given theta is the same as the products of these n terms, where we have the normal distribution, the normal PDF with yi or yn, given this function fx, fx is xn transpose theta. We already did that in the iPad, and with the variance sigma squared. For now, let's not bother too much about sigma squared. Let's assume it's known, given to us. Right now, this is the expression that we want to calculate. Now, what is the PDF for a normal distribution? Does anyone remember that? What is the PDF of a normal distribution?
Exponential minus x square by sigma square.
Yes. Does this expression look like something you've seen earlier, but it's hard to remember? Right. So 1 over sigma root 2 pi, or 1 over root 2 pi sigma squared, exponential of minus half x minus mu by sigma the whole squared, right? So this is when the random variable is x. Right? So we firstly directly apply the log to the likelihood. We transform this function. We do the negative log likelihood, right? Maximizing the likelihood is the same as minimizing the negative log likelihood, because log is a monotonically increasing function. Maximizing a function and minimizing the negative of it, the same thing. So minus log of the likelihood is the advantage we are also getting, is that the product of these terms gets converted to the summations, right? So minus summation of log probability, log PDF of a single point, right? So that's what we can say. And since we're using a Gaussian or normal likelihood, we can write that the logarithmic of, so we've seen this particular form, right? So let's say that if you had to take an exponential, so if you had to take a logarithmic of it, right? What are you left with? Logarithmic of this, half x minus mu upon sigma squared, right? And here x is a random variable, but in our calculations, x is not the random variable. What is the random variable? Y, right? So therefore, the log likelihood for a, okay, so log PDF for a single example is minus 1 over 2 sigma squared. And the terms in the exponential have just come here, right? Yn minus fx the whole squared, right? Plus there are some constants. Does everyone understand how we're getting this specific term? Right. So again, go back. If you had to take a logarithmic of this, you're left with some constants you don't care about, and you're left with x minus mu and sigma squared, right? X minus mu upon sigma whole squared, right? Now replace x with y, because our random variable linear regression is y, and replace mu with f of x, right? That's the mean of the function. And that's how you'll get log likelihood is equal to a function of yn minus xn transpose theta the whole squared. Right? And we can then, that this is for a nth point, ith point or nth point, but then we have to sum, to calculate the negative log likelihood, we have to sum it over all the n examples. Therefore, we'll get the negative log likelihood as 1 over 2 sigma squared. Assume sigma to be a known constant. Don't worry about it. So 1 over, let's assume it's 1. So the loss that we're getting is 1 over 2 summation n equal to 1 to capital N yn minus xn transpose theta the whole squared. What does this remind you of? What does this remind you of? So this is yn, and what is this thing? Sorry. This is f of x or y hat. right? Can we just call it y hat of the nth point, right? So yn minus y hat of n, right? That is the error. Yn minus y hat is the error. It's actually, let me not write it. Yn minus yn hat is the error. You have squared the error and then you've taken a mean of it. So if you find out the error, square it and mean it, what do you get? Mean squared error. You go in the opposite direction. When the term is defined as mean squared error, first you have the mean, then you have the square, and then you have the error. But actually, when the calculation is being done, calculate the error, yn minus yn hat, do the square of it, and then take the mean. Now, is this the same as the loss function which Ashish had discussed in the previous session, in the previous sessions? So isn't this kind of magical that we get the same answer? Yes. But here you didn't have to think of the loss function explicitly. You just got this as a consequence of trying to maximize the log likelihood, or minimize the negative log likelihood. So you can do the derivation. I can just skip over the maths, right? There's an analytical solution available. If you want to fit the parameters theta, it will come out to be x transpose x inverse times x transpose y. Right? It's sophisticated term. I'm not going to cover. Sorry. Where are we taking the mean? N equal to 1 over capital N. I mean, you can just divide it, but it won't change anything. Right? The loss function will still be the same. The mean is generally better because it's contained. Okay, let me actually ask that question. So why might we prefer mean squared error over sum of squared errors? Do you understand the difference? Mean squared error. So find out the error, square it, and then you can sum it over n data points, or you can find the mean over n data points. Why do you think sometimes mean squared error? So why would you prefer mean squared error over the sum of square errors?
Sir, may I try to answer this question?
Okay, just one second. Someone online is speaking. Yes, Rohit.
Yeah, sir. Yeah, it's good. Sir, it's because that, let's say we have for one thing we have 5 examples, and for another we have 10 examples. So when we want to try to compare the sum of square error, it won't be very visible. But if we try to compare mean square error for these 2 cases, we can actually compare.
Yes, excellent. So the sum of square error is going to scale in terms of the number of data points that you have. If you have more data points, the sum of squared error is going to increase, right? But the mean squared error is not likely to be that way, right? So that's the difference. So mean squared error will be more bounded that way. You can just divide it by the number of samples. It won't make a difference, right? So I'm not going to walk over the derivation. It's fairly simple, but in the interest of time, we don't need to do that. I'll go over the notebook again. So here we started off with X. We started off with this problem of X and Y, right? We had this data set. Now we're trying to figure out the best set of parameters for the linear regression here, right? We could analytically derive the answer theta MLE as X transpose X inverse times X transpose Y, right? Sophisticated expression, but let's not do it this way. We'll just use this as a ground truth, let's say. So firstly, given an X, if you remember, I just added a column of ones to X, right? So X extra becomes I cannot just show. Right? So X will become something like this. X becomes a matrix with n rows, which correspond to n number of samples, and 2 columns here. You already had 1 column, but you have added an additional first column of ones. Why have we done that? Because fx is x into theta, x transpose into theta, right? So to incorporate the theta naught term, the bias term, right? It becomes more efficient to just directly do x extra into theta, x extra transpose into theta, right? And now we can also directly compute the cost function by, if you look at this, we first compute f given a slope and an intercept. The f is slope into x plus intercept, right? And the likelihood is just the normal with mean f, and the scale is the noise scale. And then we figure out the negative log likelihood, right? So negative log likelihood, and then we're summing it up over the n examples, right? And then it becomes a cost function you're trying to optimize. And we can in fact see this animation also, right? So we have two parameters, the intercept and the slope, right? We'll see that as we'll vary these parameters. And on the right hand side, you're seeing the contour plot. How many of you have seen contour plots? Did Ashish show them yesterday? Or? No. How many of you have seen war movies or movies in which they go to certain mountain ranges? They're trying to, let's say India is trying to prevent itself from getting attacked from neighboring countries. You have probably seen some movies, like Lakshay, for example. So you might have seen. Sorry. Okay, maybe this is a good enough example for us to see. Not a very high resolution image. So if this is some 3D surface you have, and think of it as you're trying to view it from the top. Or if this is some 3D surface, right? If I view it from the top, so each of these values have constant height, right? And in the Z plane, right? That's what I'm looking at from the circle, right? That's the way we interpret the loss function. So in this case, can you tell me where is the loss the lowest? At what values? Looking at the right side plot, for what value of slope and intercept is the loss the lowest? So what value of slope? Let's ask. Slope is? Okay. So let's see if I increase the intercept, let's see what happens to the line. So it seems that we're getting better. So we're getting better in the sense that the loss, you can see the loss by this color, right? As we move towards darker shades of blue, we are getting into better zones, right? This seems like a good fit, reasonably good fit, right? But let's see if we increase the slope, what happens? It seems we're getting better, right? We're moving towards the global, we're moving towards the optima. And this perhaps seems to be a very good solution, 4 and 2.5, right? So this is the optimization problem. We need to update the parameters corresponding to the intercept and the slope so that we can get a solution which is somewhere in, which is this minimum of this 3D function, right? Negative log likelihood. That's the objective. And that we can do by gradient descent. And then for algorithms, for certain problems like linear regression, we have closed form solutions. Yes. Other questions? Okay, so then what is the regularization view in linear regression? How do we add regularization? For adding regularization, what did we do previously? We had to add a prior, right? So linear regression is highly susceptible to fitting to the data. Right? If the data itself is problematic or if the data set is small, then our fit is not very good. Right? So can we, okay, so let me ask another, let me actually go back to this. So I want you to focus on the left-hand side plot, this plot only. Right? As I vary the degree, what do you think happens to the train error? Sorry? Yes. So if I increase the degree, just look at what happens to the train RMS. It's gone from 2.1 to 1.84. .77. Okay, it's not directly exhibiting what I'm trying to show, but in general, as you increase the degree, you'll see that the train RMSE reduces because you're able to fit each and every point in the training data set very well, right? So that's the other interpretation of overfitting. You're fitting extremely well to the training data set, right? But that means that you're not generalizing well. You are looking at the each and every possible nuances of the data set, but you're probably using a very sophisticated function to do that. That's why you are overfitting. So overfitting is also known as high variance. Does anyone know why this specific term is being used? Yes, but what is the relation? What do you understand with the term variance? Yeah, so that's, but that you can, that definition you can get from overfitting also. Why is it called variance? High variance. It's not consistent with. Okay. Yeah. So all of you are roughly giving the correct answer. Let me actually share this and so let's say we had fitting a very high order polynomial. We had some data set. So I'll create some copies of this data set. Right. So in the first copy, and I want you to see this carefully, I am maybe removing a couple of points. In the second copy, maybe I'm removing some other points. So maybe if it's a very high degree polynomial that I'm trying to fit, on the left hand side, maybe I'll get something like, right? For the right hand side, maybe I'll get something like, right? Now, with the addition of even addition of movement of slightly 1 or 2 points, my function is highly varying, right? It's very, very varying. So therefore, if I had 1 point in the vicinity of this, it will lead to a very variable amount of prediction, right? Because even my model is so sophisticated, so complex, that it will learn very highly varying solutions for even slight adjustments to the data, right? That is known as high variance, right? What about if the model is very, very simple? We call the model to be highly biased, high biased. You might have heard of this term, high bias, high variance. What do you think high bias means? Why is it called high bias or underfitting? So you're making very biased, wrong assumptions about the model complexity, right? It will lead to a lot of bias. Yes. Yeah, you won't be able to, because the model is not complex enough to be able to learn certain kinds of functions. Right? So that was just about the fact that overfitting is also called high variance. That's what I just wanted to explain, this specific aspect. But coming back to the question, we had previously seen that adding regularization by the form of penalty, by adding some penalty will help to make this function smoother, right? And will reduce amount of overfitting. Yes. So what is the Bayesian interpretation of adding regularization? If we just fit to the data, right? We just fit to the data, we end up with overfitting or high variance. In order to do that, in order to reduce the fitting, overfitting, we have previously added some penalty coefficient. Now, what should we do in this using the Bayes rule so that we get a comparable effect? What should we do? Does everyone get the question? Sorry? I think you're saying correct answer. Go ahead. Yes. So again, coming to Bayes theorem, we have something like P of theta given the data is equal to probability of data given theta. This is the likelihood term, this is the prior term, this is the marginal likelihood of the evidence term, right? So we previously maximized the likelihood that gives us theta hat MLE. Right? Theta hat MLE corresponds to what loss in linear regression? Yes, you know the answer, but I think you're a little tired now. Sorry, mean squared error, right? Theta hat MLE corresponds to the to minimizing the mean squared error or the sum of squared errors. Now we want to add some regularization. So we have an additional P of theta term. If we maximize the posterior, right? Do we get some kind of a regularization as we did for the coin toss, right? So let's assume that we put some prior distribution on theta, right? So here putting a prior distribution on theta means zero variance. B square means we make this assumption that the theta values will most likely be zeros, right? Or they're most likely to be zero, but they are Gaussian distributed, right? About mean zero, right? Theta naught is normally distributed with mean 0 and variance 1 or variance b squared. Similarly, theta 1 is normally distributed with mean 0 and variance b squared. Right? That's a simple prior assumption that we take. Now the question is, so why don't you actually try this out on your own? So find out the theta hat map, right? I don't want you to find the solution. Find out the loss corresponding to maximizing the posterior. Yes. Can you find out the loss corresponding to maximizing the posterior, given that the prior is normal distribution with mean 0 and variance b squared? The prior is on the parameters theta. Are there any questions from the online audience? No? So if you saw the expression for log likelihood, you just need to add log prior to it and you're done. Log likelihood plus log prior gives you the new loss. Actually, in the interest of time, I think I can just show you the solution. You have the log joint. Previously also, if you remember, we had the log joint, right? It's equivalent to the log likelihood plus the log prior plus some constant, right? We're not considering the denominator term. We're just assuming it to be constant for now, right? Now, this is the function you're trying to maximize, right? The posterior is what you're trying to maximize, or the log posterior is what you're trying to maximize. Log likelihood we've already seen, right? So theta hat map is the argument of negative log likelihood of minus of log likelihood plus log prior. Now we can just compute the gradients with respect to theta, set them to 0, the same procedure that we've done before. The only interesting thing change here is that what is log of p of theta, right? So firstly, can you think of, let's go back to the normal distribution again. Right now, in this particular case, what do we have the normal distribution over? What are the parameters of the normal distribution? Or what is the random variable for the normal distribution? Theta, p of theta is normally distributed with mean 0 and some certain covariance, right? So you replace x with theta, mu with 0, sigma with b, right? So you'll get something which is e to the power minus half theta squared, or equivalent of it, right? You don't get theta squared because theta is a vector, right? So instead of theta squared, you'll get theta transpose theta, right? That's the expression of theta squared for vectored inputs. So that's that's it to it. That's the only thing you need to add. So you had the previous expression 1 over 2 sigma squared, and you had the summation yi minus x and yi hat squared, right? Plus 1 over 2b squared theta transpose theta. This theta transpose theta over 2b squared is coming from log prior. Right? Prior is normally distributed with mean 0. Prior is normally distributed with mean 0 and covariance b squared times identity matrix. Correspondingly, if you just fit in the formula which I'd shown from the Wikipedia page, you'll get that the loss function is summation yi minus yi hat squared plus 1 over 2b squared theta transpose theta. Can you just assume now lambda equal to 1 upon 2b squared, right? If you do that, what do you get? What kind of regression is this? Sorry? Linear regression with what penalty? Linear regression with L2 penalty, which is ridge regression, right? Instead of p of theta, let me see if I have it or not. I don't want you to show the working. So I assumed here p of theta, theta to be normally distributed with mean 0 and covariance b squared, some normal distribution, right? If I had chosen b to the p of theta to be some other distribution, right? Let's say I want to recover lasso or L1 penalty, then what should be p of theta? So it should be e to the power something, because you're doing log prior. So you just need to tell me e to the power, it should be what? E to the power minus the modulus of theta, right? Or the L1 norm of theta, not the modulus, right? And that is known as the Laplace distribution. Right? Does this look like something? If you applied a log over, you will get the L1 penalty, right? So in summary, we have normally distributed prior, right? And normally distributed likelihood, right? Gives you ridge regression, right? If you don't consider prior, if you just consider the maximizing the likelihood, you just get the vanilla mean squared error as the loss function. and Laplacian prior with the normal likelihood gives you the lasso regression, right? So you didn't have to use as such any specific variation of, you don't have to specifically mention the regularization. You get that directly as a prior here in the distribution, right? So it's kind of a very cool concept that both of these views can match. You get the effect of regularization by accordingly choosing the priors. Any questions in this? So I'm sensing everyone is now getting tired, but I still have content to cover. So you'll have to bear with me for a few more minutes and we'll very quickly run over logistic regression now. That's already covered, so I don't need to go into a lot of details. So it's a logistic regression is a classification problem. As Ashish also mentioned, the name is a misnomer. It's a classification problem, not a regression problem. Let's say you want to classify between oranges and tomatoes. Here it seems very obvious. You can see that if the radius is of that particular fruit or vegetable is greater than a certain unit, it's an orange, otherwise it's a tomato. So don't think about the physical interpretation of this is just some fake data. Actually, I'll draw this graph again with indicating y equal to 1 for oranges and y equal to 0 for tomatoes, right? But we have already done, so our aim is to be answering questions like, what is the probability of getting an orange? Let me call it an orange, because I'm looking at probability of y equal to 1. That's what we did in linear logistic regression. Probability of orange given a certain radius equal to radius, right? So in general, we want to be able to answer questions like, what is P of y equal to 1 given capital X equal to X? Like something like this. Can we fit a linear regression line through it in order to answer this question? Why not? If you move one orange point to the right, the line changes. Secondly, can you see that one of the orange is now going to be misclassified, right? Thirdly, linear regression will give you outputs which are in what range? Minus infinity to infinity, right? It's just theta naught plus theta 1x, right? But probabilities have to be bounded between 0 and 1. So how do you convert something which is between minus infinity to infinity between 0 and 1 using sigmoid? But before sigmoid, don't you think this is a better function to use for classification? Right? It's a step function, something like a step function. Doesn't it look like a better version of sigmoid? Doesn't it look like something we should have used? But why do you think we don't use this? Okay. Yes, so that's more of an appropriate, like that's one of the, I think that's a more appropriate answer in that respect, because we want, so we want smooth functions, we want convex functions in machine learning so that they're differentiable. We can compute various mathematical properties, but otherwise this is a very nice function if we can get something like this. In fact, in things like decision trees, we would end up creating a function like this. We're not covering decision trees here. So therefore, we end up transforming the y hat that we get from linear regression to something which is between 0 and 1. We want to be looking like something like this, right? Which basically says that for radius greater than 0.5, it's an orange. For radius less than 0.5, it's a tomato. We want to get something similar to this, but still use linear regression. Therefore, the output values from linear regression that we get, we need to transform that from minus infinity to infinity space to 0, 1 space, which is via the logistic or the sigmoid function, which is of the functional form like this. You've already seen this earlier. We've seen all of these things. Could we have used some other transformation? Some of you asked. Yes, you could have, but logistic regression works. It's a known transformation. And interestingly, you can also just rearrange the terms a little. So probability of y equal to 1 given x is sigma x theta, or 1 over 1 plus e to the power minus x theta. And again, there's a bit of abuse of notation. So we can interestingly also write as x theta is equal to log probability of y equal to 1 divided by probability of y equal to 0. Right. So previously we had y hat equal to x theta. Now we had log of p of y1 divided by p of y0 is equal to x theta. So this is also known as log odds. Anyone who has done betting, who plans to do betting, I don't suggest you do, but in betting, these are the terms to use. Odds. What are the odds of someone winning the match? So log odds is x theta in logistic regression. What is the decision boundary for logistic regression? Did we already cover this? Yes, what do you understand by decision boundary? So the decision boundary is when both the classes, class 0 and class 1, are equally likely, right? If both the classes are equally likely, then probability of y equal to 1 is the same as probability of y equal to 0 equal to 0.5. And what is log of 1? 0. X theta equal to 0 is the decision boundary. Right. So the other question was, could we use this squared error loss in logistic regression? Can we use that? In fact, if you try, it will probably work out okay, but it's not a convex function. So this is how the loss function looks like for if you use squared loss on logistic regression problem, the classification problem. So you can see that there are a lot of local optima. You'll probably get stuck while using gradient descent at one of these local optima. Right. Therefore, you end up using what loss? What loss do we use for logistic regression? We see binary cross entropy, and we'll see why we get that. And what is the procedure that we use to obtain the loss? Maximize what? Maximize what? The likelihood, right? Now, what is the likelihood for the logistic regression problem? So likelihood is P of D given theta. We again apply what? IID assumption. So we can break it down as the product of probability of yi given xi and theta. Now, if we can figure this expression out, we are done, right? So where y is either 0 or 1, right? So yi is going to be, so the true value is going to be either 0 or 1. So I want you to think for a minute and see if you can write this expression. There is some notion of Bernoulli that we'll be using. So this problem, if you're able to relate to the coin toss problem, then you have solved the problem. So in coin toss, you knew whether a particular coin toss was a head or a tails. You knew whether it was a 0 or a 1. And here you know that the ground truth for a ith example is either 0 or 1. Can you use that information to somehow get the likelihood? You want me to repeat? In coin toss, we had individual data items as the coin tosses, and we knew that it was either a heads or a tails, 0 or a 1, right? And we use that information. Here we know that y, the ground truth for a particular class, for the particular sample, is either 0 or 1. There is that correspondence. There we had the probability of heads is equal to theta. Here we have the probability of yi given xi and theta. If we just figure out these two terms, we are done. Just one second. Yes. Yeah. That's yeah. So it's almost on the right track. If you just write out the whole expression, you're done. But you're on the right track. Okay. In the interest of time, let me show you the solution. Probability of yi. Let's just look at one example for now. So let's forget about the pi term here, which is the multiplication of across n examples. The probability of yi given xi and theta is phi I hat, right? This is 1 over 1 plus e to the power minus xi transpose theta, right? So this is sigmoid of xi transpose theta, right? Or this is just yi hat, right? Does everyone follow that this is yi hat? So I've written yi hat raised to power yi multiplied by 1 minus yi hat raised to power 1 minus yi. How is this similar to the coin toss that we'd written? Xi transpose theta, right? And the ground truth there was heads or tails, right? And here the ground truth is yi. It's either 0 or 1, right? Should I repeat this? So in coin toss, right? If you look at this particular highlighted line. In the coin toss, probability of D1 f x was either 0 or 1, right? Was theta to the power x raised to power 1 minus theta to the power 1 minus x, right? So theta is the probability of heads, right? Or probability of heads is denoted as 1, probability of class equal to 1, right? Probability of 1, probability of class 1, let's just say that way, right? Theta to the power x is either 0 or 1, right? We come back to logistic regression. This is yi hat. What is yi hat? Probability of class 1 given the sample xi and the parameters theta, right? That's yi hat raised to power yi. Yi is 0 or 1 depending on whether it's class 1 or class 0. Right? Does everyone see the analog between these two? Yes. So, right. So yi hat, the yi hat that you're getting is going to be between 0 and 1. It's not exactly, you don't keep this value as either 0 or 1. Yi is either 0 or 1. Yi hat can be any number between 0 and 1. Right? Does everyone get this? Do you want me to repeat? This is the last thing. So I can repeat the same thing till 5:30. I can go on loop if you want to. I don't want to, but if you want to, I think we can. Let's go back to the coin toss. Okay, this is not the coin toss. Probability of D1 is equal to X. X can be heads or tails. Heads is 1, tails is 0. Is theta to the power X. So theta is the probability of heads. So probability of heads times X and then multiplied by, let's just forget the multiplied by term. So let's just look at the first term. If we figure that out, the second term comes naturally. So this is probability of heads, and heads is class 1, equivalent to class 1. Raised to power X. X is whether it's actually class 0 or class 1, right? X is either class 0 or 1. In logistic regression, yi hat, so we'd written it this way, right? Yi hat. Now, do you remember? Probability of y equal to 1 given an input x is sigmoid of x theta equal to 1 over 1 plus e to the power minus x theta, right? So this particular term, we can also just call it as yi hat, or probability of y equal to 1, right? Probability of y equal to 1, and in the coin toss, probability of heads. Are these two terms the same? Yes. Raised to power x, x is whether it's a heads or a tails, and raised to power yi, where yi is either 0 or 1. Right? Do you follow now? If anyone is confused, I can still discuss, and if anyone is still confused, I can discuss it after this lecture also. If you're feeling a little shy, that's okay. This is a slightly harder concept. It took me a bit of time. It took me a non-trivial amount of time also to understand this. So no worries on that. But once you've written this particular expression, you're done. This is the log, this is the likelihood. If you get the log likelihood and you get the negative log likelihood, you'll get the cross entropy loss. You'll get this cross entropy loss. Yi times log of sigma xi, sigma x theta is 1 over 1 plus e to the power minus xi transpose theta. So yi log yi hat plus 1 minus yi log of 1 minus yi hat. Cross entropy loss. Binary cross entropy loss. This is the binary loss. And similarly, if you were to choose a prior on the parameters theta, if you choose normal prior, you'll get L2 loss. You'll add the L2 penalty. Otherwise, you'll add the L1 penalty, and you're done. Right? So this is how you obtain the loss function for logistic regression. Similarly, we'd obtain the loss function for this is the MLE solution. We can get the map solution also. Right. So I think it's already been a lot. I should end here. I can take any questions, and we can have firstly questions based on this slides. But if there are other questions, I'm happy to answer them also, and then we can break. Yes. Okay. Any online questions? Yes. 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 Okay. So the question is that in neural networks, we use ReLU, which is fairly sharp, right? So why do we use that? Sorry. So so there are advantages. I think the question is, we use sigmoid specifically because we wanted something which is smooth, convex, like which leads to smoothness, right? So that we can do the differentiation, etc. With ReLU, we clearly know that the derivative is not existing at one particular point. So why do you think we use that? No, so I mean, so ReLU is clearly better than sigmoid in various ways and works out. But I think the question is from the perspective of the optimization, so of the differentiability. So ReLU is clearly not differentiable at that particular point at x equal to 0, right? Why do we? Sorry. Yeah. So ReLU gives the maximum value. That's so the ReLU is maximum of 0, z. So ReLU of z is maximum of 0, z. That's the functional form. So for z less than equal to 0, you get 0. For z greater than 0, you get z as the value, and correspondingly the gradients also you can obtain. The gradient, so the question is that the gradient is not defined at z equal to 0, right? Why do you think we still end up using it? Anyone from the audience, anyone from the online audience? Sorry. So one, if you don't want to be using ReLU, there are other variations of ReLU like leaky ReLU, GeLU, CeLU. Like you can just come up with. No, these are actually names. So CeLU activation. Right. So you have these various activations. So if you can see that ReLU is very, very sharp. There is some LU also, some CeLU also, some leaky ReLU also. There are quite a bunch of these. So I'm not fully sure of the exact answer, but I think what happens is when the gradients are numerically being computed, like the function is written in such a way that the gradient is directly being told to you. For anything greater than, so anything in the vicinity of z equal to 0, right? It's the gradient will be like it will be approximately 0 only, right? So that way you can define it, whether it's coming from the fz equal to z part or whether it's coming from fz equal to 0 part, it won't matter that much. So numerically, I think it works out. Okay, that's my guess. But anyone else has any better answers on this? Any thoughts on this? So I think as an exercise, what you folks can do is to use your favorite optimization library, let's say whether it's PyTorch or TensorFlow or JAX, and try and find out the gradient at z equal to 0 for a function like ReLU. See what you get. Do you get not a number? Do you get not defined, or you get something specific? Right. That exercise should just clarify to you. I think you'll get a number. You won't get not defined. Yes. Other questions? Need not be specific to this because I think this will take some time for you to process. Any other question? Yes. 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 So we'll do that today evening itself. We'll put all the slides which Ashish had used. We'll check with them. We'll put my slides. We'll put all these notebooks there already on the GitHub repository. We'll share all of these. And I was also discussing with a few students. We'll probably also share a couple of other resources. So how many of you think you'll benefit if we shared something on probability distributions? Yes. So does now everyone agree that it's important that it's useful to know a little bit more maths than what we think initially think?
Yeah. Yes, sir.
Right. So the question is that for linear regression, we have an analytical solution, which is x transpose x. So theta hat equal to x transpose x inverse times x transpose y. That's the analytical solution. Or we could use gradient descent, right? Now, the important thing to note here is that this particular cost function is convex, right? You could have used gradient descent and then you could have also used second order methods. Here, it doesn't make sense to use second order methods. Does anyone know any second order method, optimization method? Yes. Again, I think all of you have studied this in maths, but you're forgetting it. Newton's method, Newton-Raphson method to find out the root. So there's a beautiful video from 3 Blue 1 Brown, which talks about the Taylor series. Again, Taylor series you studied, right? But what is the use of it? So, but if you understand the Taylor series and understand in the context of machine learning, that how do you use it to understand gradient descent? I think that's the missing link. So we don't have enough time today, but I can perhaps share some resources on that. So that's how the link is being built. But the question was, there are many ways to solve linear regression. Which of them do you use? Generally, you end up using iterative methods. Specifically, now this is a convex problem. You'll get the same solution irrespective, unless you have chosen a very low learning rate or you've chosen a very high learning rate. You'll come to the same solution. Now you never actually end up solving the problem as x transpose x inverse times x transpose y, because that's poorly conditioned. So poorly conditioned means that the numerical algebra routine will end up not very accurately giving you the answers. So let's see. So there's this nice blog on why shouldn't I invert that matrix, right? So there's a bunch of math that you can read about numerical errors and computation. So instead of writing np.nil.invert a and multiply that with b, right? So this is a inverse b, right? You can write a inverse b in this form. It's always better to write it in this way: np.nil.solve a comma b. Now, many of us might be happy that if we write the code this way, right, it's a one-shot method. It's a one-shot code. You don't have to write a loop, right? But you may be disappointed to know that internally this will still be using some kinds of loops to solve for using iterative methods to find out the solution to this problem, ax equal to b. So eventually you end up using iterative methods a lot. So I think there's no silver bullet, there's no correct answer, no specific answer, but generally people end up using the iterative methods for such thing. And in the case of so like you never want to be inverting x transpose x inverse. Now there's another way to think about this problem, is to think in terms of the time complexity. You can actually figure out that if you were to do x transpose x, what is the time complexity for multiplying these two matrices? Then inverting is n cubed if for an n cross n matrix, and multiplying that with x transpose y, then there is some specific cost. Versus if you were to do stochastic gradient descent, then what is the time complexity required? To add another dimension to it, stochastic gradient descent has also got certain convergence properties, that how many iterations, how does it converge with respect to the number of iterations? Right. So a bunch of things I've told you that you shouldn't be worried about, especially for those who are studying machine learning for the first time. Use gradient descent. This other question, was there any question online? Is there any other way we can help you in this summer school? Of course, we won't get you pizzas, but is there any other way we could help you? Okay, I think everyone, maybe they have questions, but I think they just want to, I think it's a good time to break. Yeah, sure. Should I stop sharing? Okay, stop sharing. You can start.
Nipun, if I can, I just had to echo what you said, that please provide us feedback. And this is a 2-week-long school, and we'd like to do course corrections to make things more enjoyable, more comfortable for you. Please let us know.
Yeah, sure, sir. Thank you very much. Yeah, I will.
Right. So this is also as Anirban was saying, this is also an experience for us. Every time we are trying to modify content to make it more accessible. So in fact, so that's why I was also attending the first few sessions to understand that how is everyone responding to questions to the content. And then I changed my content. I would have probably given something else. Right. But getting feedback from you would be very useful. What was useful, what was not useful, what was hard, what was easy. Like what could be speed up, what could be go slow, and if the code useful, is the Discord discussion useful, things like that.
So I thought I would leave you with something to think about. So I'll just give you one scenario. You are in a casino and you are playing very simple game. It is with a fair coin. So I've already given you that it is a fair coin. Okay. So that prior is set now. And you are playing this game and continuously for 9 times you are getting only tails. And you can only get reward if you get heads. Okay. So what do you think will be the probability of heads if last continuously 9 tosses were tails? So how many of you think that probability of heads will be more if last 9 tosses were tails? You can raise your hands. 1, 2, 3. And how many, like, okay, you can give answers in numbers, let us say. What do you think will be the probability of heads? Half? Why? Someone wants to explain. Yes. So this is very related to the IID thing we discussed, right? Because you are having the same distribution, you are just tossing the same coin. So it does not depend on the last 9 trials that you have, right? And this is something known as the gambler's fallacy. So you can search about that and you will see something interesting on that.